Hello. So we are going to have a look at electrostats solutions for the relevant questions in CET test 2. Here we go. A charge of q coulomb is placed on a solid piece of metal which is having an irregular shape. So it is not a regular shape like a cylinder or a sphere, but it can be my favorite shape of a potato, right? So this is a metal. So I place q coulomb on it. What will happen to the charge? The concept underlying is this. Only when it is having a uniform shape like a sphere, the charge will distribute itself uniformly on its surface. You won't notice any charge getting excessively clumped up or very, very far from each other at places. Everywhere, the charge will be distributed uniformly. But when it comes to this potato shaped and random shapes, there you will see that only at the edges, wherever there are sharp edges, there some charges will be in excess, where at the other places where the surface is smooth and even, you can have charges placed at a far distance from each other. So the logic is charge will not distribute itself uniformly, but it will distribute in such a way that the each of these charge would like to stay as far as possible from each other. So it would always like to be like everything in nature. It will always like to be in a state of minimum energy. So it will distribute itself such that the potential energy of the charges is minimized to ensure minimum repulsion. In a sphere, there is no other way. It has to distribute uniformly because the surface itself is uniform. But in such a random shape, surface is not uniform. So it will distribute in such a way that the repulsion is minimized, and as a result, charges will be far away from each other. We know that potential energy is K, Q1, Q2 by R. If R is more, U will be less. So one goes with C. An interesting question, right? Question number two. Question number two is based on NCRT lines or NCRT summary, especially the golden points we discussed in the class. At the 6 points about the conductors, electric field near a conducting surface is always perpendicular to the conducting surface. If it is positively charged, it will be outwards. If it is negatively charged, it is going to be inwards. So what is the electric field then? It is going to be sigma by epsilon naught, and it is always normal to the surface, right? There are no calculations involved here. It is a summary point fact way of for valid for every conductor. Here it is a uniform surface charge density. We can also have our potato shape where we can say sigma is a local charge density, but here it is uniform surface charge density, good for us. Nevertheless, it is sigma by epsilon naught normal to the surface. Then the third question is based on wherever I see a parallel plate, trigger word, it must be a capacitor. In a capacitor, they have given the potential difference between the plates is 50 volts and the distance between the plates is 5 mm. There is a charge which is entering, let us say with some velocity 10 power 7 meter per second. Q of the charge is given, mass of the charge is given. They're speaking about the acceleration. What is going to be the acceleration of this? Well, we know first of all, acceleration is always independent of velocity. Well, for what forces? For all forces like electrostatic force and gravitational force. Regardless of velocity, acceleration exists. Acceleration does not depend on velocity for electrostatic and gravitational forces. Therefore, velocity data is irrelevant in the question. It's not needed at all. You may be confused to use it, so don't bother. Don't use it. So acceleration is going to be QE by M. Very nice. But Q value is given, M value is given, but you do not have the value for electric field. Now, how to find electric field? Well, we have potential difference and distance to the rescue. We know that E is equal to V by D. Electric field is always equal to potential gradient. Therefore, we replace E with QV by MD and see that outrightly we have all values with us. Charge is given, mass is given, potential is given, potential difference 50 volts and D5 mm is given. You put in the numbers, do the calculation, you get the right key. So this is the approach, the physics of the situation is this. You put in the numbers, you'll get the right answer. Now we move on to question number 4. In question number 4, there are two unlike charges. Trigger word, very, very careful, unlike. Therefore, one should be plus, other should be a minus. Both of them have same magnitude, so plus Q and minus Q, separated by a distance of 2D. Fine. What is the potential at a point midway? Here you should remember, we have discussed in the class too. Potential formula is V equal to KQ by R and Q should be substituted with its polarity. You should always consider the sign whenever you're dealing with potential and potential energy. We have a good news. The good news is the distance of this point from each of the charge is same, as well as the charge magnitude is same. So potential due to one of the charge will be kq by say d. The other potential would be k times minus q by d. When you add them, you get perfect cancellation, right? So potential midway between them is always zero. Here, you should know you need to put sign into the picture, and the question is made in a such a way that everything cancels. It is exactly symmetrical. The point lies in a zero potential uh, uh, region. Now, question number 5. Three charges are placed. Okay. In on the vertices of equilateral triangle. Fine. What is the net potential energy? Right? Three charges are placed, L, 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 it seems, and let us say it is Q, Q, and Q. Hold on. Potential energy means I need to make as many pairs as possible from the question. So it should be KQ square by L plus KQ square by L plus KQ square by L. I can make three pairs. So there should be three somewhere in the options. The only option which has three in it is C. So the right option should be C. Now we move on to question number 6. In question number 6, two spheres of radii A and B, right, are charged and joined by a wire. The ratio of electric field of the spheres is, well, they have not mentioned whether this is a metallic sphere or not. Is made of wood? Is it made of plastic? We don't know. So if they are made of insulator and connected by a wire, nothing would happen much. Okay. But now let us assume they are metallic. I have two spheres. One is having radius A, other is having a B, and I connect a wire in between them, right? And what is the ratio of electric fields? They should be the question should be more clear after joining. After joining the two spheres by a wire. Well, we know something. We know that once a wire is connected, both of them will settle down to the same potential. They settle down to the same potential. And we can use this uh, relation. Since it is a sphere, I will use a concept of spherical capacitance and say Q equal to CV, where C is capacitance of each of them. Okay. And what would be the ratio of the electric fields now? So we go like this. Okay. Q equal to CV is what I would use. Now, what is the final charge on this sphere? It would be C1V, charge on the first sphere. Charge on the second sphere would be Q2, would be C2V. Both have same potential. What is electric field? Electric field is KQ1 by A square for the first. Electric field for the two is KQ2 by uh, B square, because it is a sphere. So for a sphere, we can always assume the charge is at its center. If the entire sphere can be replaced with a point charge at its center, so we can use these two formulae. Well, now if I put these respectively into the expression, I get E1 by E2 should be equal to, and you should know what is expression for C1. Capacitance of a a spherical capacitor is always 4 pi epsilon naught R. So for this sphere, it is 4 pi epsilon naught A. For this sphere, it's going to be 4 pi epsilon naught B. Fine. So I put the numbers. When I put the numbers, I will have B by it should depend on B by A. You can check this yourself. You take the ratios, it should depend on B by A. I have made it as simple as possible, something which can be tackled with, the 1 minute kind of approaches. Otherwise, it's going to be very tricky if you bring in every time formulas, and formulas, right? The key concept is once you connect with a wire, both have same potential. We can use Q equal to CV and then later electric field relation. Now, question number 7. Two charge spheres, area 10 and 15, connected by a thin wire. No charge will flow if they have. Right. No charge would flow if both of them have the same potential. The condition for current or charge to move is there should be a potential difference. If potential difference is zero, then the charge would not move. So both of them should have the same potential if charge is not supposed to move. Now question number 8. In question number 8, there are two spheres, A and B, respectively, at the same electric potential. What is the ratio of surface charge densities of A and B? Fine. So what I'm going to do is we know potential of a sphere is always equal to KQ by R. Potential of the first sphere is going to be V1 KQ1 by A. Second sphere is going to be V2 KQ2 by B. What I understand is both of them are at the same electric potential. So this and this expression should be the same. So Q1 by A should be equal to Q2 by B. All right. Now they're asking what is the ratio of surface charge density. What is surface charge density? It is for the first sphere, it is Q1 by 4 pi A square. I will just write A square because 4 pi is going to get cancelled anyway. For the second, it is Q2 by 4 pi B square. Now I take the ratios. This goes up, this goes over here. So it is Q1 by A square times B square by Q2. But from this relation, I have Q1 by Q2 should be equal to A by B. It should be, this can be replaced as A by B. When you place it as A by B, again, you get this as B by A. Since they are at the same potential, I can use the potential of a sphere, simple formula, KQ1 by A equal to KQ2 by B. So Q1 by A should be equal to Q2 by B. They are not interested in Q as such. They want to know how it is distributed. Surface charge density is charge by area. So therefore, we have Q by A square over there. Now the ninth one. Ninth one is a hot favorite of many CET Comet K examiners. Identical drops thing. There is a trick which I will reveal soon, but without the trick, let's try to handle this. N identical drops. Whenever I say drops, I will assume they are spherical drops. So whatever holds good for a sphere, area, volume, etc., I can apply it for this also. When combined to form a large drop. So there are N identical drops. Combining one large drop, the potential is found to be 40. What is the value of N? Many things coming over here. So let us say there are N drops. It is getting merged into a single drop. The volume of these N drops put together is N into 4 by 3 pi R cube, where R is the radius of one small drop. That should be equal to the volume of this big, because volume didn't go anywhere. Water didn't evaporate. The drops volume remained constant. So 4 by 3 pi R cube, where capital R is the radius of the final drop. I cancel 4 by 3 pi's on both sides. So I have N times R cube is equal to capital R cube. All right. But now their thing is something different. They are telling that voltage of one of the drop is 10. What is voltage of one of the drop? Let's see that. voltage of just one of these drop, V1, is going to be KQ by R, where Q is the charge on that one drop, R is the radius of that one drop. And when it combined, it seems it got another voltage, 40 volt, which is K times. You see, there are Q, 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 Q. Totally, there are N Qs. So total charge is going to be NQ by the capital R, which is this. So I have got three equations with me now. First is N times small r cube is equal to capital R cube. Then they have given V1. V1 is to be 10. V2 is 40. So with the help of these, I can figure out what is the unknown value that is namely capital N. So there are three equations. You need to eliminate the variables, arrive at the value of N. Can you substitute? Yes, you can substitute only if you have come so far. So once I divide these two, I will divide these V2 by V1. If I do, it will become 4 by uh, uh, N into R by R. 4 is equal to N into R by R. But for me, what is R by R? From this, R by R whole cube is going to be 1 by N. So therefore, R by R is going to be 1 by R by R is going to be 1 by N power 1 by 3. So it is going to be 4 equal to N power 2 by 3. Right? Now find the value of N. What number, or if I take, well, raise both sides to power 3 by 2, so 4 power 3 by 2, 4 power 3 by 2 would give 8. So I get the value of N as somewhere around 8. So this is the concept involved. It will be useful if you try to quicken up your calculation and do this really in the exam hall. Otherwise, if you want to remember formula, well, it will take a lot of more efforts to remember formulas and get this. But the element is this. Element is volume conservation. Volume is not going anywhere, and charge is also conserved. Whatever the charge is on these n drops, the same charge is on that one drop. Now, going on to 10th one. 10th one is relatively easy. They have potential difference V is given. What is the final speed of electron? Wherever potential difference and final speed is there, we always go to energy conservation and say half mv square should be equal to E into V. QV is a potential energy. E is a charge on the electron. So straight away, V should be equal to 2 EV by M under root. So C is the right choice. Potential gradient, fellows, is always dV by dx, dV by dr at any distance. This basically gives you electric field. Electric field is a vector, therefore potential gradient is a vector. Now question number 12. They're comparing various works. Whenever these sorts of questions are given, comparing work done in carrying a charge, always remember the path independent nature of electrostatic work done, which means the work done in carrying any charge depends only on the initial location and final location. Well, I'm carrying a charge Q along, let's say, this path through Q, from here to here. Plus Q is at the center, right? Now, A is at the same distance as Q was from this capital Q. So initial potential energy is the same as final potential energy. Therefore, the work done by me would be zero. Why? Because this point and this point are at the same distance from the center, right? So yeah, so that would be most late. If I place plus Q there, I would say both points are at the same distance from the center. So hence, I can argue that the potential energy did not change, right? Uh, it is to be moved. The electric field is at plus Q. So it is to be moved from the Q is to move from this point to this point. So work done would be same everywhere. And I will see that the plus Q is almost at the center, right? If it's at the center, all the distances, this distance, and this is going to be the same. Potential energy is not changing at all. Therefore, the work done is equal and all of them are equal to zero. That is one solution we can arrive at. Path independent nature depends only on the initial configuration and final configuration. Question number 13 now. Question number 13 again. Equipotential lines. Do not confuse this to be electric field lines. It is equipotential surfaces. How do you get the magnitude of electric field from equipotential lines? Well, we know that E is equal to dV by dx, right? I will ignore the negative sign for the time being because they're asking the magnitude. So here we have the concept that whenever distance between the equipotential surfaces is less, their electric field is maximum. So I just need to see between this and this surface, it's sort of very huge distance. Between this and this surface, huge distance, but between this and this surface, distance is less. And what about dV? dV is the potential difference between the surfaces. Any two surface you take, potential difference is always going to be 50 minus 40, which is again 10, 40 minus 30, 10, 30 minus 20, 10, 20 minus 10, 10. dV is same. So what determines electric field is the separation between the surfaces. So it is actually B. Now 13 goes for B. Well, now 14th one. 14th one is a fun question. Electric potential, keyword electric potential, not field, and it is a charged metal sphere, not just a sphere, it's a charged conductor, right? So when I go from center to the surface of a conductor at any point, field is zero and potential is constant. Do not confuse these two things. Many people think potential is also zero. No, potential is constant, whereas field is zero. So which of these graphs shows constant potential till R, the radius of the sphere? It is only A and C. I can eliminate B and D. Further, after crossing the sphere, what would happen? After the point is outside the surface of the sphere, the entire sphere would behave like a point charge located at the center. Now, what is the potential formula? V equal to KQ by R. So voltage would vary with the distance like Y equal to 1 by X or like a rectangular hyperbola. Definitely not linear like C has shown. Therefore, the right answer is A. 14 goes with A. Now going to the 15th one. The 15th one is actually a demonstration performed by Faraday 300 years ago. There's a conducting shell of a radius B. Inside it, I place one shell of a radius A. Both are conductors, and this has a charge of Q on it. It seems after I connect them with the help of a wire. I can either connect them with the help of a wire, or I can simply, you know, make them touch each other. That is not at all an issue, right? So once I do it, both the inner sphere and the outer sphere becomes one big conductor. It becomes a system of conductors, one big conductor. Earlier, if A is held away from B, then the issue is different. But A and B are in contact with each other. Hence, A and B together forms one big conductor. So what would happen? We know that charge cannot stay inside a conductor. So whatever charge was there on the inner sphere, it will zap, go through the wire or through the contact and reach this outer surface of the outer sphere. So the entire charge will go from the inner sphere to the outer sphere. So right option would be A. Now, if an electron moves in a direction of electric field, then what will happen? Tricky. Electron moves in the direction, right? That would mean electron's motion is like this. We know that electron always experiences a force opposite to direction of electric field. So its force experienced by will be in this direction. speed, velocity will be in this direction. As a result, what will happen? Electron will always slow down. In other words, its kinetic energy is going to come down. According to conservation of energy, if kinetic energy comes down, definitely potential energy has to go up. So kinetic energy will decrease and potential energy will increase. Another way of looking at it is wherever the electric field is pointing, that is always in the direction of decreasing potential. So if the electric field is pointing this way, potential is potential over here is always greater than potential over here. Now, what if I place an electron here? Remember, electron has a negative charge. Potential energy is Q into V. If Q is negative, if V1 is greater than V2, then on a number line, if you see, then electron's potential energy at the first point is going to be lesser than electron's potential energy at the second point. Therefore, potential energy decreases as electron moves from 1 to 2. Energy conservation, kinetic energy shall increase. A hollow conducting sphere, so and so, fine. There's no need to do anything other than remember that a conductor is an equipotential surface. So the total potential at A, B, and C has to be the same. Now going to question number 18. In 18, they are asking rank the pair of plates according to the highest to the least. The concept electric field is given, equipotential surfaces are given. So how to arrange E equal to dV by dx, and the distance dx is same between the plates. So what matters? Wherever potential difference is maximum, their electric field is maximum. Again, I'm omitting the negative sign because they're asking magnitude only. So what is the difference between these two? 110. Difference between these two, 50. Difference between the voltages of this 100. So the least is 2. Which of the options has least as 2? It is A and D. Highest is A. Highest is 1. So 1 is highest, 2 is least. So therefore 18 goes with D. The electric potential is given as this. What about its equipotential surfaces? Potential will be same as long as x coordinate remains same. Among all the surfaces here, where would be x coordinate remaining same? X coordinate would remain same only in the first condition where it is in the YZ plane, X, Y, and Z. If it is in YZ plane, if the surface is in the YZ plane oriented, X coordinate of all such YZ planes of all points on a YZ plane will be the same. So if x coordinate is same, potential of all those points lying on the surface will be the same. Therefore, the right answer would be planes parallel to the YZ plane. Going on to question 20. In question number 20, we are asked to find what is when is in which of the orientations is the potential energy of a dipole maximum. Okay. So either we can do it in a formula way, which in CET works, or you can do it by intuition, right? So look carefully over here. We know the formula is U is equal to minus PE cos theta. Okay, minus PE cos theta, where theta is angle between dipole moment and electric field. Here, dipole moment and electric field are opposite to each other. So theta becomes minus 1. Here, dipole moment and electric field are in the same direction. Therefore, theta here becomes 0. Here, theta becomes pi or 180 degrees. That's all I need to know, because I know cos theta gets its maximum and minimum at 1 and minus 1 respectively. So potential energy will be maximum whenever cos theta takes minus 1, since minus into minus will become plus. See, if cos theta is minus 1, then minus PE into minus 1, which is PE. PE is always greater than, when you put 1 over here, it will be minus PE. Therefore, at theta equal to pi radians, the dipole will have the maximum potential energy. Okay. So this is just the fundas from the fundas of potential energy of a dipole and how to measure it. It depends on the angle between electric field and dipole moment. You should see carefully in all examples as to how dipole moment is oriented. It is always from negative charge to the positive charge. Here it is 180, here it is 0. Be careful. That's all I need to know because cos theta takes maxima at cos theta minus 1 and 1. I won't even look at this case and this case. It is irrelevant to me. So this was the CET electrostats solutions. I hope this has been some use to your understanding. Learn it 360 degrees, all aspects, and let's meet with more physics in the class. Take care and thank you.